Hi, this is the video for section 3.2 of A Student's Guide to the Schrödinger Equation. This section is called What the Schrödinger Equation Means, and in it we're going to talk about each term in the Schrödinger equation as well as what the collective combination of those terms tells you about the behavior of quantum wave functions. It starts off with this, as I call it, expanded view of the Schrödinger equation, and the terms are all defined here. Psi, of course, is the quantum wave function. This is the one-dimensional case. Later on in this chapter, you'll see this for the three-dimensional case. If you've tracked through the earlier chapters, you realize that I is, of course, the imaginary unit, the square root of -1. H bar is Planck's modified constant, that is, h over 2 pi. And this partial derivative is the rate of change of that quantum wave function psi over time. On the other side of the equal sign, this m refers to the mass of the particle or system that is described by the wave function psi. And this second spatial derivative, as you're going to see in this section, going to be a fair amount of discussion of that as the curvature of the wave function over space. And finally, V is the potential energy in the region of interest. For the next few pages, each of those terms is explained in succession. I think these descriptions are fairly self-explanatory, so I'll just tell you the highlights of each one. In this first one, for example, we mentioned that since psi is a function both of space and time, this has to be a partial derivative. In other words, it's measuring the change of psi with time only. In each of these sections, I also like to talk about the units of that term. We're going to see in a later chapter that psi represents a probability density amplitude, the square of which has dimensions of probability per unit length. And that's the same as 1 over meters. So psi squared has units of 1 over meters. Psi must have units of 1 over the square root of meters. That's in the one-dimensional case. And of course, that means that its derivative with respect to time has units of 1 over seconds times the square root of meters. I is, of course, the square root of -1. It's the complex operator. If you read that bit in Chapter 1, specifically Figure 1.7, you see that multiplying by I is equivalent to a 90-degree rotation in the complex plane. The reason it's significant in the Schrödinger equation is because it means that quantum wave function solutions may be complex. You'll see the impact of that in Chapters 4 and 5. No dimensions associated with the factor I. H bar is the modified Planck constant. It's just h, the Planck constant, divided by 2 pi. And just as h is the constant of proportionality between energy and frequency, h bar is the constant of proportionality between energy and angular frequency, where omega is 2 pi f. You can also think of h bar as the constant of proportionality between momentum p and wave number k. The reason I mention these two equations in talking about h bar is because it's through those that h bar appears in the Schrödinger equation. It appears on the side of the equation with the partial of psi with respect to t because that's the total energy side, which has an h bar omega. And on the other side of the equation, the square of h appears in front of the second partial term with respect to x because it's in the momentum equation, and the kinetic energy goes sp squared. So that's why h bar appears in the Schrödinger equation. Its units are talked about here. H has dimensions of energy per unit frequency. That means that h bar has units of energy per unit frequency per radian. In the SI system, those units turn out to be joules per hertz per radian. The numerical values of h and h bar in the SI system are given here. The m term is pretty straightforward. It's the mass of the particle or system that has wave function psi, and its units are kilograms in the SI system. As I said earlier, the second derivative of psi with respect to x, we're going to talk about quite a bit in this chapter. And of course, it's a partial because psi is a function of both space and time. First derivative with respect to space gives the slope of that function, and the second gives the change in the slope. That is the curvature of the wave function. And since psi has SI units of 1 over the square root of meters, when you take that second derivative with respect to space, you get 1 over meters to the 5/2 power. That leaves only the potential energy term V, which could vary over space and time. So in some cases, you'll see it written as V of x and t, or in the three-dimensional case, V, which depends on the position vector r and time. Another little warning about the difference between potential and potential energy in quantum. V refers to potential energy. This paragraph points out a couple differences between classical and quantum, including the fact that in classical mechanics, potential, kinetic, and total energy have precise values, whereas in quantum mechanics, it's only the expectation or average value that you're going to get to know. And in classical mechanics, the potential energy can never be greater than the total energy, but in quantum mechanics, the total energy may be less than the potential energy. A little more explanation of that here, in which we talk about those as being classically unallowed regions in which E is less than V. And the wave function behavior is going to be very different there from the behavior in classically allowed regions where E is greater than or equal to V. When we talk about the stationary solutions of the time-independent Schrödinger equation in the next section, you're going to see that the difference between the total energy and the potential energy determines the wavelength of oscillating solutions in the allowed regions and the rate of decay of the solutions in classically unallowed regions. And of course, being a potential energy term, this has dimensions of energy and SI units of joules, which are kilograms meters squared over seconds squared. So that's what the individual terms mean. The equation as a whole is described as a parabolic, second-order, partial differential equation. And each of those terms is described here and why this equation qualifies. Differential, of course, because it describes the change in the wave function over space and time. Partial, because it's a function of two variables, some derivatives with respect to time, some with respect to space. It's second order, because the highest derivative, in this case the second order spatial derivative, is a second derivative. That makes it a second order differential equation. And finally, parabolic, because that combination of a first order term and a second order term is analogous. It's not the same as, but it's analogous to the equation of a parabola, in which there's a first order algebraic term y and a second order algebraic term x squared. That's the equation for a parabola, and that's why this is called a parabolic equation. So that's what it's called. What does it really mean? I think the best way to understand that is to compare it to this equation from classical physics, which is called a diffusion equation. There's some other names for it down here. And what does that equation describe? A couple of examples I give here are concentration of a substance or the temperature of a fluid. And in the diffusion equation, the proportionality factor between the time derivative on the left and the second order spatial derivative on the right is capital D, which is called the diffusion coefficient. So how does that compare to the Schrödinger equation? Well, here's the Schrödinger equation in a region in which the potential energy is zero. Notice one thing that's slightly different from the previous version. I've moved the I from the left side to the right side, where it's 1 over I, and that's the same as minus I, which cancels the minus sign. So this is the version of the Schrödinger equation that looks most like the diffusion equation. But there's a key difference, and that key difference is in this term. That factor of I has very important implications. In spite of that difference, I think it's still helpful to understand what the diffusion equation is telling you. And to understand that, imagine that this is some function of space and time. We're looking at time t equals 0. And this function has some curvature along the x-axis. Notice the slope is positive here and getting steeper. That means positive curvature. The change in the slope is positive, going from small positive to bigger positive. Past this inflection point, the slope is positive, but getting less steep. So therefore, the second derivative is negative there, because the slope is becoming less positive. On this side of 0, the slope is negative, but becoming steeper. Therefore, the curvature is negative. The slope is getting more negative with distance. But beyond this inflection point, the slope is negative, but becoming less negative. So there, the curvature is positive. So, in this region, positive curvature. In this region, negative curvature. In this region, negative curvature, and in this region, positive curvature. So why is that worth knowing? Because the curvature tells you how the function is going to change over time. Where the curvature is positive, the time change is positive. So here we said the curvature was positive, it's going to grow. Here the curvature is negative, going to decrease. Negative, going to decrease. Positive curvature here, going to increase. So at some later time t, the function has diffused or spread out. And you can tell which direction that's going by looking at the curvature in each region. Now, you have to be careful when you try to apply this to quantum mechanics. You say, oh, so does that mean that any wave function will diffuse or spread out in space as time passes? Well, sometimes it does, but not always. And why is that? That I in the Schrödinger equation means that the wave function solution can be complex. And that allows not only for diffusing behavior, but oscillatory behavior, as you're going to see in later chapters. But this is probably a good time to ask, so what exactly is it that is spreading out or oscillating? That is, what does psi represent? It was mentioned just briefly earlier that it was Max Born who said that wave function psi might be a probability amplitude. This is fundamental to the Copenhagen interpretation of quantum, which you can read about in Chapter 4, but in there you'll see that a Born rule says it is psi squared, that is the square of the magnitude of the particle's wave function in position space, that gives you the probability per unit length of the particle existing in some region. So if you integrate that probability density over some interval, you get the probability of finding the particle within that interval. So when we talk about the wave function oscillating or diffusing, it's the probability distribution that is changing. Another paragraph here about why it's helpful that the Schrödinger equation has first order time derivative, because that means if you know the wave function at some instant, the Schrödinger equation tells you how the particle's wave function will evolve over time. That's consistent with the Schrödinger equation representing all you can ever know about the state of a particle or system. Now, if you've taken a waves class, you may have seen the wave equation with second-order partial derivatives in both time and space. So couldn't we just take another time derivative here and get something that looks more like the classical wave equation and is even more useful? Not really. As you know, when you take this wave function second time derivative, you're going to pull down another factor of omega, and that omega is proportional to the energy. So the equation you'd get if you took that second-order time derivative would have an energy in one of the terms. And if you're asking why that's a problem, just remember, equations of motion such as Newton's second law, they relate force and acceleration and mass, but they do not contain the energy. They work no matter what the energy of the particle is. So we don't want terms containing energy, momentum, or velocity appearing in our equations of motion. So we don't want that second-order time derivative. So the bottom line is, we can't derive the Schrödinger equation from first principles, but its form does make some sense. Specifically, it allows us to predict and describe the behavior of quantum particles and systems. And a very useful form of that equation is the time-independent Schrödinger equation, which is the subject of the next section. That's it for this one.